Welcome to Understand the Math. In this video, I'm going to walk you through exam questions on vector spaces. I'll summarize the steps needed to solve each question and carefully work through every detail so that you'll feel confident tackling these problems on your own. Let's get started. In this problem, we're given a set H, and we're asked to determine if H is a subspace of R2. There's 3 steps that we can follow to determine if a set is a subspace. The first step is to check that the set contains the 0 vector. The second step is to test for closure under addition. And then the last step is to test for closure under scalar multiplication. I always begin these problems by letting any vector in the set be equal to x and then writing down what x is equal to. According to our h up above in our problem, our vector x is the vector x1 to x2, where x2 is equal to x1. Let's go ahead and plug that in. So we get that vector x is equal to x1, and then for x2, we're going to plug in that x2 is x1, so we get a 2x1. So any vector in our set is in this form. Let's begin by checking that our set H contains the 0 vector. So we're going to check if our vector x is equal to 0. Looking at this form of our vector x, we can see that vector x is going to be equal to the 0 vector if x1 is equal to 0. So if we plug in x1 is equal to 0, we get that x is equal to 0, 0, which is the 0 vector. So let's write down that our set H contains the 0 vector. Now let's go ahead and let's see if our set is closed under addition. To do this, what we're going to do is we're going to create 2 vectors that are just like vector x. I'm going to call the first vector u, and I'm going to let it be equal to u1 to u1. Let me go ahead and highlight this up here so you can see that this is our vector that is any vector in our set H. And then let's call our second vector v, and we're going to make it look just like H, except instead of an x, we're going to have a v. So we have a v1 and a 2v1. To check if it's closed under addition, what we're going to do is we're going to take vector u and we're going to add vector v. So this is going to be if we add the first component, u1 plus v1, and then the second component is 2u1 plus 2v1. And then I'm going to go ahead and rewrite this as u1 plus v1, and then 2 times u1 plus v1. Now what we have to do is we have to see if this vector looks like our vector x that I highlighted above in green. And you can see that if we were to set x1 equal to u1 plus v1, these 2 vectors will be exactly the same. So this tells us that our set H is closed under addition. Now let's go ahead and let's check our third condition. Our third condition is that we have to check for closure under scalar multiplication. This one's actually easier than checking for closure under addition. All we have to do for this one is we're going to take a scalar c and we're going to multiply it by our vector u that we created in step 2. So this becomes c times u1 and then c times 2u1. I'm going to go ahead and rewrite this. The first component stays the same, and then I'm going to write the second component as 2 times c u1. then what I'm going to do is I'm going to set x1 equal to cu1 and look back up to our vector highlighted in green and see if it's the same. And it definitely is. So that tells us that our set H is closed under scalar multiplication. Because our set H contains the zero vector, because it's closed under addition, and because it's closed under scalar multiplication, we can conclude that H is a subspace of R2. In this problem, we're given a matrix A and a vector W, and we're asked to determine if W is in the null space of A and if W is in the column space of A. Before we solve this problem, I want to go over a little bit of theory so that we can understand what we need to do. W is in the null space of A if matrix A times vector W is equal to the zero vector. So what we're going to have to do is we're just going to have to check if A times W is equal to 0. So let's go ahead and let's do that. Our A times W is equal to our matrix minus 12, 48, minus 3, and 12. And we multiply that by vector W, 4, 1. And what we get is a minus 48 plus 48 for our first component, and then a minus 12 plus 12 for our second component. And you can see that this is equal to 0, 0. And this is our zero vector. So we can conclude that W is in the null space of matrix A. Now let's look at the column space. W is in the column space of A if W is a linear combination of the columns of matrix A. What we mean by a linear combination is that W is C1 times A1. Well, let's go back up here. Let me go ahead and let's label this. This is going to be A1, and this is going to be A2. So our W would just be a linear combination of the columns of matrix A. To check this, what we're going to do is we're going to take A1 and A2. Those are our columns of matrix A. We're going to augment it with W, and we're going to put it in echelon form, and we're just going to see if a solution exists. Remember, echelon form is the form that we have to reduce our augmented matrix to if we want to see what type of solution we have. I'm going to begin by putting the columns of our matrix on the left. So this is a minus 12, minus 3. And then our second column is a 48, 12. And then on the right, we're going to have our vector W, which is 4, 1. Let's go ahead and circle our first pivot. When I look at row 1, I notice that every entry in row 1 is a multiple of 4. So I'm going to go ahead and start by taking row 1 and replacing it with row 1 divided by 4. Let's see what this gives us. We're going to take every entry in row 1 and divide it by 4. So we get a minus 3, a 12, and a 1. And then we notice that our second row is exactly the same. Whenever you have a repeat row, you know that when you do row reduction, that row is going to go to 0. So let's go ahead and let's do that. This becomes minus 3, 12, 1. And then our second row, all the entries are equal to 0. So let's circle our pivot. We have one pivot, and then we have a row of all zeros. And we have a column that's missing a pivot. Because we have a column that's missing a pivot, we're going to have infinitely many solutions. So our augmented matrix has a solution. In fact, it has infinitely many solutions. Because a solution exists, this tells us that W is in the column space of A. In this question, we're given a matrix A, and we're asked to do two things. The first thing is that we're asked to find the null space of A, and then a basis and geometric description for the null space of A. And then after we do that, we're going to find the column space of A and a basis and geometric description for the column space of A. Let's go ahead and let's start with the null space. Let me first define what the null space of a matrix is. The null space of A is all vectors X such that A times X is equal to 0. So to find the null space, what we're going to do is we're going to take our matrix A, we're going to augment it with 0, and we're going to put it in reduced echelon form and find our vector X. Let's go ahead and let's write down our matrix A. We have 1, 3, 5, 0, 0, 1, 4, minus 2, and we're going to augment this with 0. Now we have to go about putting it in reduced echelon form. You might notice when you look at these pivots that our matrix is already in echelon form. So all we have to do is one more step to put it in reduced echelon form. And that step is going to make that entry equal to 0. So our row operation is going to be that we're going to take row 1 and we're going to replace it with row 1 minus 3 times row 2. Let's see what this gives us. I'm going to copy down our second row first. And now let's find our first row. This is going to be a 1, 0. We're going to have a 4 times a minus 3 is a minus 12. Plus 5 gives us a minus 7. And then we're going to have a minus 3 times a minus 2, which is 6. Adding that to 0 gives us a 6. And then our right-hand side is 0. Let's now circle our pivots. And those are the variables that we're going to solve for. So from our first row, we get x1 minus 7x3 plus 6x4 is equal to 0. And then from our second row, we're going to get x2 plus 4x3 minus 2x4 is equal to 0. Now let's go ahead and solve for x1 and x2. Our x1 is going to be 7x3 minus 6x4. And then our x2 is going to be minus 4x3 plus 2x4. Now what we're going to do to find our basis and a geometric description and to find the null space is to write our answer in what we call parametric vector form. So to do that, we're going to start with our vector x. We have 4 columns, so our x has 4 variables, x1, x2, x3, and x4. And then we're going to just plug in what we get. We found that x1 was 7x3 minus 6x4. Our x2 was minus 4x3 plus 2x4. And then this is the part where students always get confused. x3 is a free variable, so it goes in as itself. And same with x4, there is no pivot in x3 column or the x4 column. So those are our free variables and they go in as themselves. And there we have our x. Now what we're going to do is we're going to split this apart. We're going to have one vector that is a multiple of x3, and that's going to be a 7 minus 4, a 1, and a 0. And then we're going to have x4 multiplying the vector minus 6, 2, 0, 1. We can now write down what the null space of our matrix is. So the null space of A is going to be all the linear combinations of these two vectors right here. So we often write that in terms of the span. So the span of a set of vectors is all the linear combinations of those vectors. So we can say that the null space is the span of these vectors. 7 minus 4, 1, 0. And then the second vector that we got, minus 6, 2, 0, 1. So that's what the null space is. Now we can find the basis for a null space, and this is the really easy part. The basis for the null space is just these two vectors right here. So let's write down the basis for the null space of A is equal to, and then instead of writing the span, we're just going to grab these two vectors. 7 minus 4, 1, 0. And then minus 6, 2, 0, and 1. So that's our basis for our null space. Now the last part we have to do is the geometric description of our null space. So notice in the basis for our null space, we have two vectors, and they are both vectors in R4. When we have one vector, our geometric description is a line. When we have two vectors, our geometric description is going to be a plane. And then if we were to have three vectors, our geometric description would be 3D space. So we have two vectors, so we can conclude that our geometric description is equal to a plane in R4. This just helps us really visualize what our basis looks like. Let's now look at the column space of a matrix. Little bit of theory first. The column space of a matrix A is all the linear combinations of the columns of A. And then the basis for the column space of A is just the pivot columns of matrix A. Let's first write down what the column space of A is. It's going to be all the linear combinations of the columns of A. So we just go back up to our matrix, and we're going to grab all the columns of matrix A. Let's go all the way back up here. Got to go all the way back. So notice that we have 4 columns. 1, 2, 3, 4. So those are the columns that we're going to put in our column space. And we have all the linear combinations of those columns. So I'm going to erase this, and I'm going to write this as the span of these columns. So our first one was 1, 0. Our second one was 3, 1. Our third one was 5, 4. And then our fourth one was 0, minus 2. I probably should have put this in red, and I didn't. So what I'm going to do is I'm just going to highlight this so you can see that that is our solution for the column space of our matrix A. Now we have one last thing to do. Our last thing is to find the basis for the column space. So to find the basis for the column space, we have to put A in echelon form. So let's go back up here where we had our matrix A. I'll put a little star here so you can see where we're looking. And notice that our matrix is already in echelon form. We had 2 pivots, so those are our pivot columns. So when we go back up to our original matrix, these columns are going to be the basis for our column space. So let's write that down here. Let's go all the way back down to the bottom. And let's write down that the basis for the column space of A, I'm writing in red this time, is going to contain our first two columns, 1, 0, and 3, 1. One thing to keep in mind is that you always have to have the original columns of A, not the columns of A in echelon form. Now, in this example, they were the same, but if they're not the same, just make sure and go back and grab the original columns of matrix A. Now we have one last thing to do, and that's to find the geometric description. Notice that we have two vectors in the basis for our column space. So that means our geometric description is going to be a plane in R2. In this problem, we're going to determine if the following set of vectors is a basis for R3. Before we begin, I want to explain what it means for a set of vectors to be a basis for R3. A set of vectors is going to be a basis for R3 if the vectors are linearly independent and the vectors span R3. So there's actually two things that we're going to have to check. The way that we're going to do this is we're going to let A be a matrix with columns containing the four vectors right here in our set. What we're going to do then is we're going to take matrix A and we're going to put it in echelon form, and we're going to look at the pivots in our rows and our columns of our matrix in echelon form. If every column has a pivot, we'll know that our set is linearly independent. And if every row has a pivot, we'll know that our set spans R3. And if both of those two are satisfied, we can know that the set of vectors is going to be a basis for R3. We're going to start by forming our matrix A, and what we're going to put in matrix A is the vectors that we were given. So our first vector is 1, minus 2, 3, and then we have a 0, 3, minus 1, and then a 3, 8, 4, and then lastly a 0, a 2, and a minus 2. And what we have to do is put this in echelon form. So I'm going to go ahead and I'm going to circle our first pivot. And what we have to do is get a 0 below those pivots. So we're going to do some row replacement, and we're going to take row 2, and we're going to replace it with row 2 plus 2 times row 1. And then we're going to take row 3, and we're going to replace it with row 3 minus 3 times row 1. Let's see what this gives us. Our first row is going to stay the same. And then our second row is going to become a 0, a 3. We have a 3 times 2, which is 6, plus 8 gives us a 14. And then we have a 2. And then let's go ahead and let's go to our third row. We're going to multiply our first row by minus 3, add it to our third row. So we get a 0, a minus 1. We then have a 3 times minus 3 gives us a minus 9, plus 4 gives us a minus 5. And then because of a 0 there, our minus 2 stays the same. Now let's look at our next pivot. This is our next pivot. And I notice that below it, our pivot is equal to negative 1. So what I'm going to do is I'm going to take row 3, and I'm going to replace it with row 3 divided by minus 1. And then let's go ahead and let's switch rows 2 and row 3. And we'll go ahead and write this down. Our first row stays the same. Our second row is now our third row multiplied by a negative 1. So we have a 0, 1, 5, 2. And then our third row is what our second row was. 0, 3, 14, 2. Hang with me, we're almost done. We're going to circle this pivot, and then we're going to get a 0 below this pivot. So our row operation is going to be that we're going to take row 3, and we're going to replace it with row 3 minus 3 times row 2. This is what our matrix now looks like. Our first two rows are the same. And then our third row is going to change. We're going to get a 0, 0. We have a 5 times a minus 3 gives us a minus 15, plus 4 gives us a minus 1. And then a 2 times a minus 3 is a minus 6, plus 2 gives us a minus 4. Now let's circle our pivots. And now let's go back and find out exactly what we're asked to solve for. Often when I get done with a row reduction, I'm like, oh my gosh, what were we actually solving for? So what we're doing is we're trying to determine if this set of vectors is a basis. So we have to check if every row and column has a pivot. So let's look at our rows first. I'll go ahead and I'll highlight those in green. And you can see that every row has a pivot. Let's go ahead and let's write that down. Every row has a pivot. So that means that our set spans R3. And now let's look at every column. That's the one I think we're going to run into trouble with. We have a pivot in this column, and this column, but we do not have a pivot in our fourth column. So let's write down that every column does not have a pivot. So that means that our set is not linearly independent. And because of that, we can conclude that our set is not a basis for R3. Because one of our requirements was not met. In this problem, we're asked to find the dimension of the subspace spanned by these following vectors. Let me tell you what we're going to have to do to solve this problem. The first thing that we're going to do is we're going to create a matrix A with columns that contain these vectors. We're then going to take our matrix and we're going to put it in echelon form, and then we're going to count pivots. The number of pivots is going to be the dimension of our subspace. Whenever I teach linear algebra, I always find that this problem is one of the most missed problems. And I think it's because it's just hard to figure out what you actually have to do. So let's go ahead and let's do this. We're going to take our matrix A, and we're going to let the vectors that we're given form the columns of this matrix. So we have a 1, 0, minus 3, a 2, 1, minus 5, a 5, 4, minus 11, and then our last one is minus 4, minus 3, and 9. And we're going to put this matrix in echelon form. I'm going to go ahead and circle our first pivot. And what we're going to have to do is we're going to have to get a 0 below that pivot. So we're going to use a row operation. We're going to use a row replacement. And I'm going to take row 3, and I'm going to replace it with row 3 plus 3 times row 1. Let's see what this gives us. Our first two rows are going to stay the same. Let's now look at our row 3. We're going to have a 1 times a 3 gives us a 3 minus 3 is a 0. And then we're going to have a 2 times 3, which is 6, minus 5 gives us a 1. And then we have a 3 times 5 is 15, minus 11 gives us a 4. And then lastly, we have a minus 12 plus 9 gives us a minus 3. Notice that our third row is a duplicate of our second row. So that row is going to go to 0. So let's go ahead and let's mark that. We're going to get 1, 2, 5, minus 4, a 0, 1, 4, minus 3, and then a row of zeros. Now let's go ahead and let's circle our pivots. And we can see that our matrix is in echelon form, and we have 2 pivots. So we have two pivots. And that tells us that we have two linearly independent vectors. So that means that the dimension is equal to 2. The dimension is just the number of linearly independent vectors in a set. In this problem, we're asked to find the rank and nullity of a matrix A. Let's start by looking at some definitions. The rank of a matrix is the number of pivot columns in that matrix. The nullity of a matrix is the number of free variables in a matrix, and that's just the number of columns without a pivot. We then have what's called a rank theorem, and the rank theorem states that the rank of a matrix A plus the nullity of the matrix A is the number of columns of A. That's because the number of pivot columns plus the number of columns without a pivot is just equal to the number of columns in the matrix. When we get a problem like this, what we do in practice is we're going to take our matrix A and we're going to put it in echelon form, and then we're going to count the pivots and then count the free variables. And that will tell us what the rank and nullity of the matrix is. So let's go ahead and we'll start by writing down our matrix A. When you recopy a matrix, be sure to be very careful. I often find that students will make a mistake in the original recopying of the matrix. So here's a hint that might help you. What I typically do when I do this, after I write it down, I glance back and I just make sure that I've copied it down right. That's a really good habit to get into. Okay, we did. So what we're going to do now is we're going to circle our pivot and we're going to get zeros below that first pivot. So we're going to use some row replacement. What we're going to do is we're going to take row 2 and we're going to replace it with row 2 plus 3 times row 1. And then we're going to take row 3 and we're going to replace it with row 3 minus 2 times row 1. And that'll make both of those entries equal to 0. Let's go ahead and let's do this. Our first row is going to stay the same. Now we're going to multiply our first row by 3 and add it to our second row, so we get a 0. We have a minus 2 times 3, which is a minus 6 plus 6 is 0. We have a 2 times 3 is a 6, minus 1 gives us a 5. And then we have a 9 plus 1 is 10. And then a minus 3 minus 7 is minus 10. Now let's look at the third row. We're going to multiply our top row by minus 2, add it to our third row, and we get a 0. We have a minus 2 times a minus 2 is a 4, minus 4 is 0. And then 2 times a minus 2 is a minus 4, plus 5 is 1. And then we pick up a minus 6 plus 8 is 2. And then lastly, we pick up a 2 minus a 4 gives us a minus 2. Now let's look at our second pivot. That's that one right there. Let's go ahead and let's make that equal to 1. So we're going to take row 2 and we're going to replace it with row 2 divided by 5. Our first row is going to stay the same. And then our second row is 0, 0, 1, 2, minus 2. And then notice, before we write down our third row, let's notice that this row is the same as that row. So that means our third row is going to go to 0. So let's just go ahead and let's do that. Let's go ahead and put zeros down here. And now our matrix is in echelon form. I'm going to circle our pivots. We have one here and we have one here. So let's notice that we have 2 columns with a pivot. I'm going to label these columns with a pivot with a P. And then our other columns have free variables because there is no pivot. So I'm going to label those as columns with a free variable. Okay, so let's go back to our original problem. They wanted us to find the rank and the nullity of matrix A. So our rank of A is our number of pivot columns. And that's going to equal 2. So our rank is equal to 2. And then the nullity of A is the number of non-pivot columns or the number of free variables. And that is equal to 3. And just to make sure, a built-in check is that 2 plus 3 is equal to 5, and we have 5 columns. So we know we've done the problem right. In this problem, we're told that A is a 5 by 7 matrix with nullity 2, and we're asked to find what the rank of matrix A is. To do this problem, we're going to use the rank theorem. The rank theorem tells us that the rank of A plus the nullity of A is equal to the number of columns of A. So let's begin by writing down that our matrix A is a 5 by 7 matrix. That means that we have 5 rows and we have 7 columns. Now let's go ahead and let's use our rank theorem. We have the rank of A plus the nullity of A is equal to the number of columns of A. So I'm going to go ahead and let's fill this in. The rank of A is what we want to know. So let's put this down as rank A. Plus the nullity of A, which we're given right up here, is 2. And that's equal to the number of columns of A, which we just said was equal to 7. So this tells us that the rank of A is 7 minus 2. And we can write down that the rank of A is equal to 5. The rank of a matrix tells us a lot of information about our matrix. Be sure to check out the next review video on eigenvalues and eigenvectors.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.